So in this video, we're going to look at 7 circle theorems that you need to know for your exam. We're then going to end the video by looking at real exam questions like this one. And I'm not going to just show you the theorem in one form. I'm also going to show you different variations of how they can give you the theorem, just so you can answer all sorts of questions. So we're going to start off with the basics of circles. So to draw a radius is just a line from the center of the circle to the circumference. So that is called a radius. A diameter is a line from one end of the circumference to the other end. So it touches the circumference on either side and it passes through the center. Now the next one is the circumference. So the circumference is this outside line there. That is what we call the circumference. A chord is a line that touches the circumference on either side. However, it does not pass through the center. If the chord passes through the center, it is then called a diameter. Okay. A tangent is a straight line that touches a curve. So a curve, in this case, a circle, it just touches the curve. It doesn't pass through it, it just touches like that. Now shade the minor segment. So you will draw a chord first. So a chord is a line where 2 points touch the circumference. The minor sector is the small bit. Okay, again, if I draw a chord here, I can draw a chord like this. Now it says the major segment. So the major segment is the major bit there, the bigger side, okay? Now for a sector is a region inside 2 radiuses. So we'll draw 2 radiuses. Here's one, here's the second. Now the minor, as you know from before, is the small one. And again, if I do the same here, if I draw a sector, which is basically the area enclosed by 2 radiuses. So I've drawn 2 radiuses, and major is going to be the major bit, which is that there. So let's start off with the first theorem. So an angle subtended by a diameter at the circumference is always a right angle. So the word subtended just means create. So essentially what they're saying is an angle that's created by a diameter. So we have a diameter here. It creates an angle. The angle the diameter creates is that one there. And that angle is always a right angle. And just to show you that in action, if I go into this example here, so if I just have a diameter like this, you can see that regardless of how I move this angle, because it's created from the diameter, it's always 90. Now, if I move the diameter, so it's no longer the diameter, because remember the diameter has to pass through the center. Now, at this point, it's not 90 anymore. So as soon as the line passes through the center, the angle that's created is 90. So you've seen it there in action. Going back here. Now, just so you're familiar with the exact wording of this rule, it has to be a diameter. So in that case, this is true. That angle there is 90. I'll just use my pen actually. That's 90. It's true here as well. That's 90 because we have a diameter that creates an angle. Again, here we have a diameter and it creates that angle there. That is also 90. Now here, notice this is not a diameter. It does not pass through the midpoint. Because it doesn't pass through the midpoint, we cannot use that rule here. We cannot say that this angle here is 90 because it doesn't pass through the center. This rule only applies when the angle is created by the diameter. Now here, the angle doesn't touch the circumference. So another part of the rule is that an angle created by the diameter at the circumference, this does not touch the circumference. So we cannot say that that there is 90 degrees. So we can't use that rule here either. I'm just being very precise here so you know exactly when this rule applies. Okay, you have to have a diameter. So diving into an example, the first one will clarify everything. So step 1, does it have a diameter? Yes, it does. Step 2, does it have an angle at the circumference that's created by the diameter? Yes, it does. So in this case, we know that's going to be 90 using that circle theorem rule. And we can say then, since angles in a circle, well, if we do 90 plus 44, we get 134. And if we do 180, take away 134, because angles in a triangle add up to 180, we get 46 degrees. Okay, so that is what x is. Now, with these type of questions, you always get marks for giving a reason. So your reason here, you would write it out. I'm not going to keep writing the reason out. Usually I'll just say it, but in this example, I'll write it out. So the reason here is that the angle subtended by the circumference by the diameter, at the circumference is 90 degrees, okay? Now, the mark scheme looks for, I'm just going to underline them as well in a different color. The mark scheme is going to look specifically that you've mentioned that word, and that word. If you have not mentioned these three words, you will not get the reason mark, okay? Just to get that one reason mark, you have to mention all three of these words. So if you look at the Edexcel mark scheme, it will specifically say that you need to mention these three words. So moving on to the next one. So the way my videos work, I'm going to do the example on the left, which is I do. You're then going to press pause and have got an example on the right. So that's your turn to have. So again, nice and easy. We've got a diameter. It creates an angle at circumference. So that's going to be 180 take away 75 plus 90. Take away sign there. That gives you 15 degrees. And remember, I'm not going to write the reason out here, but you must write the reason to get the second mark. Otherwise, you lose it. Okay. So again, I'm just showing you the same question here in a different orientation, just so you're not used to just seeing it in that one orientation. We have a diameter, and we've got to find x. So x is going to be angles in a triangle added to 180. So that's going to be 180 take away 72 plus 90, which is going to give you 18 degrees. Again, I'm not going to write the reason out again, just so to save a bit of time in the video. But again, you will write your reason, and your reason is because the angle subtended from the diameter at the circumference is always 90 degrees. And again, same thing here. So hopefully you've pressed pause now to go. So that's 180 take away. That's going to be 90, 32 minus 90 plus 90. It's equal to 15 degrees. And again, remember, you do need to state your reason. Okay, it's the exact same reason. So the next theorem, opposite angles of a cyclical quadrilateral add up to 180. Okay, so what you want to be aware of with this rule is a cyclical quadrilateral is one where all 4 points touch the circumference. If all 4 points do not touch the circumference, it's not a cyclical quadrilateral. Then opposite angles in these add up to 180. So what does that mean? If this was 100, that means this is 80. Okay, and that applies here as well. So it's always the opposite angles. So just to show you that in action again, if I head over here, if I create, for example, 100 degree, 90 degree angle here, 100 is probably better. Now you can look at the top left and the bottom right. That's 80 plus 100. That gives you 180. And if you add 96 and 84, you get 180 again. So opposite angles add up to 180. And you can move this in many ways, like that as well, just so you can see it in a different shape. And again, opposite angles still add up to 180. Okay, this is still a cyclical quadrilateral, and it doesn't apply here. At this point, it's not a quadrilateral anymore, okay? It's completely lost its shape. So, like that. So, heading back. Now, this is a cyclical quadrilateral because all 4 points are the circumference. Same with this, all 4 points are the circumference. However, here, only 3 of the points are on the circumference. So, this is not a cyclical quadrilateral. That means the opposite sides do not add up to 180, okay? This rule does not apply. So there's certain things that need to be true for that to apply. So again, here, first thing to check, do all 4 points lie on the circumference? Yes, they do. It's a cyclical quadrilateral. So x is going to equal 180 take away 100, which is 80 degrees. Y is going to be 180 take away 70, which is 110. And remember, there is a mark for writing your reason. I'm not going to write the reason here. I'm going to tell you what it is, just to speed up the video a little bit. So the reason here is because opposite angles in a cyclic quadrilateral add up to 180. Again, hopefully you've pressed pause and had a go at this. So y here is going to be 180 take away 120, which gives me 60 degrees. X here is 180 take away 130, which is 50 degrees. And remember, please, you must write your reason, okay? And the reason here is the opposite angles in a cyclical quadrilateral add up to 180. So looking at this one here, now the reason I've included this example on the left is so you can see that it's in a bit of a kite shape, just so you're still familiar. The rule, remember, applies when all 4 points of the quadrilateral lie on the circumference, which they do. So y here is going to be 180. Again, I'm showing my working out on purpose so the examiner can see what I've done, because there are always marks for methods in case I lose one. So I'm not just writing y is 100. I'm actually showing how I got there. Again, I can write x is 70, but I would rather show the examiner the working out so he can see what I've actually done. And remember, please, remember, a lot of people forget to write the reason. You need to write the reason, okay? You have to state that opposite angles in a cyclical quadrilateral add up to 180. Now, the one on the right, hopefully you've pressed pause and had a go, and it might seem a bit strange at first. So firstly, does it have 4 points on the circumference? Yes, that means it's a cyclic quadrilateral. So secondly, angles on a straight line is what we need to use here as well. So angles on a straight line mean this is going to be 180 take away 150, and we can call this y. Let's just say y is equal to 30 degrees. And what's the reason here? Again, please state your reason here. The reason here is because angles on a straight line add up to 180. And then to get x, we're going to do 180 take away 30, which gives you 150. And again, state the reason here. Now, the reason here is because opposite angles in a cyclical quadrilateral add up to 180. It's a different reason. So you're going to be stating two reasons for this one. So moving on from there. Now, this might seem a little bit different, and it might not be immediately obvious what you need to do. In your head, you should always cycle through, well, what theorem could apply here? And if you think about the cyclical quadrilateral, does it have 4 points on the circumference? Yes, it does. That does form a quadrilateral. What does that mean? Opposite angles add up to 180. So we know that this is 50. So we know this is going to be 130. So again, we can just call this y, and I'm going to show my working out again. So that's 180 take away 50. So the examiner can see what I've done there. And that gives me 130 degrees. I will also state my reason. Again, I'm not doing it to speed up the video, but my reason is because opposite angles in a cyclical quadrilateral add up to 180. And then finally, how do I find x? Now, to find x, angles in a triangle add up to 180. Now, notice this shape is a triangle. So that angle, and that angle add up to 180. So I know what we have 20. Well, we're going to do 180, which is what the angles in a triangle add up to. And I'm going to take that away from 20 plus 130, which is 150, which then gives me 30 degrees. So x is 30 degrees. Again, state your reason, because angles in a triangle add up to 180. So there's two reasons for this one. So again, hopefully you press pause and I go like this. I can just call this y, and then y would just be 180 take away 70, which is 110 degrees. And then again, please state your reason. Opposite angles in a cyclical quadrilateral add up to 180. X is going to be 180 take away 110 plus 30, which is 140, which gives you 40 degrees. And again, please state your reason. And your reason is because angles in a triangle add up to 180. Now, moving on to the next one, two tangents from the same point are of equal length. Now, what's key here is that it's from the same point. That is key. So these two tangents are drawn from the same point. If they're drawn from the same point, they're of equal length. Why does that matter? Because when they're both of equal length and we form this kind of shape, it's an isosceles triangle. If that and that are the same, that means this bit here is an isosceles triangle. So these base angles are the same. And again, just to show you that in action, feel free to head over to GeoGebra and have a look at this yourself. But regardless of how I move this, however close it is, however far it is, the radius, the tangent, where the line meets the circle, is always the exact same distance from that point. So with this one, the example is fairly simple, because if that length there is the same, and that length there is the same, because both tangents are drawn from the same point, that means this must be 50. So essentially what you've then got is this triangle, where, again, you would state your reason. So here I would write my reason, and my reason is that two tangents drawn from the same point are of equal length, and then you would also state that base angles in an isosceles triangle are the same. So that would be reason 1. You could also put reason 2. Base angles in an isosceles triangle are the same, and your reason 3 could be angles inside a triangle add up to 180. So if you do 50 plus 50, take that away from 180, and that gives you 80 degrees for x. So again, hopefully you've pressed pause and had a go at the example on the right. So it would, again, this time it's slightly different. We've been given the green angle, so that's fine. We'll do 180 take away 30. That gives me 150. Cool. And then we'll do 150, divide that by 2, because base angles in an isosceles triangle are the same. And that gives me 75. Again, reason 1, the reason this is 50 is because when the two tangents drawn from the same point are of equal length, the reason this is 75 is because, well, it's an isosceles triangle, and base angles in an isosceles triangle are the same. Remember to state your reason. So radius meets the tangent at 90 degrees. So whenever there's a tangent that touches the radius, it's always at 90 degrees. Again, just to show that in action as well. You can see that here, regardless of how I move this radius, whenever it meets the tangent, whether it's down here, up there, or up here, it's always at 90 degrees. Now, with this one, you might be thinking, well, is this not the case of where, two tangents drawn from the same point are of equal length? Yes, that's true, but there's also two radiuses here. That's a radius, and that's a radius that's touching a tangent. So they're both 90 degrees, so worth bearing that in mind here. So the first one, is there a radius that touches a tangent? Yes, there is, so that's 90 degrees. Again, you would write your reason here. Okay, you could even label this angle y. So you could say y is 90 because a radius meets a tangent at 90 degrees. So then for x, you would have 180, take away 40 plus 90, and your reason here is angles in a triangle add up to 180, so 90 plus 40 is 130. Take that away from there, and that is your answer for x. Again, hopefully you press pause and had a go at this. So first thing we can say is a reason. The radius meets the tangent at 90, which means y is 90. And then we can do 180, take away 90 plus 60, which is 150, which then gives you 30 degrees here, which is x. And then coming on to here, again, I've done this one on purpose just so you can see it's upside down and it might not be immediately obvious, but there is a radius. Remember, a point from the center to the circumference is a radius, and there is a tangent. So that means this meets here at 90 degrees. So again, state your reason. Radius meets tangent at 90 degrees. And then angles in the triangle add up to 180, so that's 90 plus 20, which is 110, so that gives you 70 degrees for x. Again, hopefully you press pause and had a go at this. Now, this is a little bit more trickier, and you might be confused with, what theorem am I actually using here? You know, is it the 2 points, the two tangents from the same point are of equal length, or am I using the fact that radius meets the tangent at 90 degrees? So the one we're using here is going to be radius meets the tangent at 90 degrees. We don't actually need the other theorem. Although the other theorem is still true, it's not that it's false. It's not that this length and this length are no longer the same. That's true. But we don't need that theorem to solve this problem. We can split this in half like this. And now what happens is if I just draw that out, the top triangle, they're both the same because I've split them in half. So whether you use the top or the bottom, it doesn't really matter. That's 90. What's half of 60? So that's going to be 30. And what we're trying to find, let's call that y for now, even though we're trying to find x. So we know that the first reason you would state here is going to be for this bit here, and that is the radius meets the tangent at 90. That's covered. Then you're going to do 180, take away 90 plus 30. Now 90 plus 30 is 120. Take that away from 180, and that gives you 60 degrees. So that's telling me that y is equal to 60 degrees. Now x is going to be twice y, because what you found is that angle there. If that's 60, this also must be 60 because both triangles are the same. So that means x is going to be 60 times 2, which is 180. Again, you can also state the fact that angles in a triangle add up to 180. But yeah, this one was a little bit more advanced. But yeah, hopefully that makes sense. And the next theorem is angle at the center is twice the angle at any point on the circumference subtended from the same chord. Again, with this question, the mark scheme specifically looks for the word circumference, the word subtended, and the word chord. If you do not mention them three words, you won't get the mark. So what it's saying is that the angle at the center is twice the angle at the circumference. So for example, if this is 50, what we're saying is this angle here is 100, given that they are subtended by the same chord. Remember, the word subtend just means to create. If I've got a line and I'm subtending an angle, that's what it means, okay? I'm creating that. I can also do that. That's also subtending an angle from the same line. So if I draw a chord for this, the chord would be here. Okay, now this chord is used to create this angle, and it's used to create the angle at the circumference. Now, so that's what this theorem is saying. So if I, again, go back to show you this in action, that would be this theorem here. If I just move this, let's just put that there. Let's put this up here. Now you can see that's 100. When that's 100, the top one's 50. So the angle at the center is twice the angle at the circumference. And if I keep moving this, notice it's still true here, even though the shape's slightly changed. The angle at the center is still double the angle at the circumference. And if I go up here, that is still true, because that is 80 and that is 90. If you double 80, if you half 180, you get 90. And if I go all the way up here, it's still true, because if I half 206, I get 103. It's still true all the way up until this point. So it could even look like that. Even in this shape, it's still true. Okay, it changes slightly when you try to do something like this. But if I keep moving that, and it's also true if you do this. even at that point, at that point, at that point, and at this point, it's true, okay? And the reason it's true is because it's created from the same chord. Now, going back to the slides, looking at these examples, just to highlight that. So, whenever there's an angle at the center, I want you to start thinking about this theorem. Because there's an angle at the center here, there's the chord for it, it's there. Does this chord also create an angle at the circumference? Yes, it does. So that theorem works here. Again, is there an angle at the center? Yes, there is. Does the chord for that angle, which is that there, does that create an angle at the circumference? Yes, it does. Again, coming down here, is there an angle at the center? Yes. Does the chord for that create an angle at the circumference? No, it doesn't. No, it doesn't. So that is not true. That theorem does not apply there. Again, coming on to this. Now, does the chord for this angle at the center create an angle at the circumference? It doesn't. Although it goes up there, it doesn't actually come back down here. The chord that's used to create this green angle is actually that one there. It's not the same chord. Okay, so this is not part of the theorem. And then finally, looking at this last one, yes, they both share the same chord, but the green angle doesn't touch the circumference. And because it doesn't touch the circumference, that means this statement's not true. So that is not true either. I just want to highlight and emphasize this so you really understand exactly when these rules apply. And here you can just see all I'm doing is I've got this shape here and I'm moving it a bit to the right just to show you that it's still true as I keep moving it down, because some people think it only looks in this shape here. With this rule, it doesn't. What you're looking for is there an angle at the center? Now, it's slightly different here. I'll come on to this later on. But the rule still applies, but there's a slight adjustment we need to make. But is there an angle at the center? Yes. Is there an angle at the circumference created by the same chord? Yes, there is. So the rule still applies. So, like I said, I'll come on to these examples later on. But for now, if you just look at this rule, is there an angle at the center? Yes. Is there an angle at the circumference that's created from the same chord? So if I draw the chord for the angle at the center, it's that one. So that means it is true. So that means x is going to be 40 times 2, which is 80. And then again, your reason is, again, you do need to hit these words. So the angle at the center is twice the angle at the circumference, subtended from the same chord. You need these exact 3 keywords within that sentence to get the mark. So that's your reason. And again, hopefully you've pressed pause and had a go at this. It was fairly straightforward. And remember, please make sure you wrote down your reason. That's 140. Moving on, so this is just the opposite. So now we've got the angle at the circumference, so we're just halving it. And then again, you've got the angle at the circumference, it's 70 divided by 2. You should show you working out like that. And please remember, state your reason, because angle at the center is twice the angle at the circumference, subtended from the same chord. And now with this one, now you might be looking at this and you're like, well, there is an angle at the center, which there is, okay? Don't think there isn't, it's right there. There is an angle. And it's actually on this side instead of this side. And now you might be thinking, okay, let's half 240 to find x. So if I half 240, I get 120. Now, if you look at x, you can tell that angle, there's no way that's going to be 120, because x looks like an acute angle. 120 must be an obtuse angle, right? So you can just visually tell there's something not right with your answer. And I want you to bear that in mind for the exam. Use a bit of logic. Does it look right? And if the answer doesn't look right, that doesn't look 120. So there's something wrong there. And then you think back to the theorem and you're saying, well, the theorem said angle at the center is twice the angle at the circumference, and they both share the same chord, which is true. So what is wrong here? Now, there's one extra bit to the theorem, right? That the angle at the center must be in a different sector to the angle at the circumference. Now, remember sectors, when I covered at the start of this video, a sector is the region formed by 2 radiuses. So this is what we call the minor sector, and the major sector would be anything outside of this. Now, the angle at the center needs to be in a different sector to the angle at the circumference. At the minute, they're both in the major sector. So I need to calculate, essentially, if I use a different color, I need to calculate this angle in red. We know angles at around a point add up to 360, so that's 360 take away 240. And if you do 360 take away 240, that gives you 120. And now you can find x. To find x, all you need to do is, that's 120, so that's going to be 120 divided by 2, That's 60. So it already looks a lot more reasonable, and your reason here is going to be angle at the center is twice the angle at the circumference subtended by the same chord. Okay, so again, with the example on the left, you can look at it, and the first one of the questions to ask yourself is, well, where's the sector? The sector's there. Does the sector have an angle in it? Or the better question to ask is the angle in the center in a different sector to the angle at the circumference? It's not. At the minute, they're both inside. If I shade it in a different color, at the minute, they're both inside the major sector. Okay, so because they're both in that, we need to then find the angle at the center in the other sector, which is just going to be 360, take away 280, and that gives you 80. Oh, let me just go back there. So if I use a different color, that means that angle there is going to be 360, take away 280, which is 80 degrees. Now that I have that angle there, we are going to say x is 80 divided by 2, which is 40. And again, your reason, please state this, is the angle at the center is twice the angle at the circumference subtended from the same chord. And again, here I'm just trying to show that the exact same logic applies. Is there an angle at the center? Yes, there is. Is there an angle at the circumference? Yes, there is. So we can use that rule. That angle at the center is twice the angle at the circumference. And please state your reason, okay? I'm not writing it just to save a bit of time on this video because it's becoming a bit long. And then again, have we got an angle at the center? Yes, we do. So x is going to be 2 times the angle at the circumference, which is given that they're both subtended from the same chord, okay? Remember that is key as well, that they are. So if I draw a line there, I can see their chord. I can see that same chord is used to create both the angles. And again, same with this. Same chord is used to create both the angles. The angle at the center is also in the opposite sector to the angle at the circumference. So that means x is going to be 80 times 2. Remember to state your reason. And here x is going to be 100 times 2, which is 200. And again, remember to state your reason. And here again, so when you look at this theorem, don't get confused. Is there an angle at the center? Yes. You should straight away start thinking of that theorem. Then, is the angle at the circumference subtended from the same chord? Yes, it is. So the angle at the circumference that I have from this chord is that one there. Remember, it has to be the one created from the chord. So you might look at the 60 and be like, well, that's at the circumference, yes. But it's not created by this chord. This chord, the angle this chord creates is that one there. Remember, the word subtend means just to create. So when you're creating something like that, okay? So x is going to be half of that, because angle at the circumference is a half the angle at the center, given they are subtended by the same chord. So looking at the next one, again, do you have an angle at the center? Yes, I do. If I've got an angle at the center, have I got an angle at the circumference subtended by the same chord? Where is my chord? Let's draw the line for the chord. The chord is there. So the chord is creating the angle at the center, which is that one there. And the chord is also creating an angle at the circumference, which is that one there. So that means x is 10 degrees, because angle at the circumference is half the angle at the center. So 20 divided by 2. And again, please remember, state your reason. Angle at the center. Right, so now this also applies when there are multiple angles. Okay, so you can have multiple angles coming off the same chord. So if I draw on my chord, step 1, draw on my chord. Is there an angle at the center? Yes, there is. Is the angle at the center and the angle at the circumference subtended by the same chord? Yes, that one is. So is y, and so is x. So what does that mean? That means x is a half of whatever y is. So 130 divided by 2, 65, and y is also equal to 65. And final check is also that they're both in different sectors, which they are, because the green bit I can see is inside the minor sector, and I can see the other two are inside the major sector. Okay, and if the green angle was inside the same sector as pink, which is the major sector, you would then subtract it from 360 to get it in the opposite sector. So again here, x is going to be a half of that, which is 60. Again, remember to show you're working out like that bit quick there. So x, so that would be 120 divided by 2, which is 60 degrees, and then y is 120 divided by 2, which is 60, and your reason is because angle at the center is twice the angle at the circumference subtended by the same chord. Now here things get a little bit more interesting because it might not be immediately obvious what's going on. Is there an angle at the center? Yes, there is. Is there an angle? And then we look at the chord. So if I draw on the chord for the angle at the center, it's that one there. Does that chord create an angle at the circumference? Yes, it does. It creates that angle there. Now, before you go in and start applying the rule of angle at the center is twice the angle at the circumference, remember the other bit. They both have to be in opposite sectors. Okay, so at the minute, if I shade in the minor sector, so remember the minor sector is created by the radiuses. So if I put a line on the radius, that's a radius, that's a radius, okay? That's telling me the minor sector, so the smaller one, is that there. Now the problem is, for this rule to apply, the angle at the center has to be in the opposite sector to the angle at the circumference. So I need to find what the green angle is in this sector. So that green angle in this sector is simply 360 take away 160, which is 200. Now, I know that's 200, so now I can use that rule. So x is going to be 200 divided by 2, which is 100. Remember, 200 is still in the center. It's just on this side of the center. And then please state your reason to get that final mark. And again, hopefully press pause and go at the example on the right, but the exact same principle applies here. So this is going to be 260. So x is going to be 260 divided by 2, which is 130. And again, remember to state your reason. And now with this, it gets a little bit different because it might not, again, be immediately obvious that you're like, well, I'm looking at this and there is no angle at the center. However, there is a point at the center and there is some sort of, the angle's not given, but an angle has been created here, even though they haven't told us what it is. So if you look at this and you think through the theorems in your head and you're like, one of the theorems I know about is something to do with angle at the center. So you know that this angle here and this angle here are linked because this angle and this angle are created by the same chord. So I know that's 50. I know that this and this length are the same. I should use a different color because radiuses, they're both radiuses. So the lines I've colored in red there are both radiuses. Radiuses are both the same length. Okay, it's the distance from the center of the circle to the circumference. It's always the same. It doesn't change. So now that I know them two, I know that this angle here must be 50 because it's an isosceles triangle. If I know that that's 50, then I know that this is going to be 80 because angles in a triangle add up to 180, which then means x is going to be 80 divided by 2, which is 40 degrees. Now, reason one is that base angles in an isosceles triangle are the same. Reason two is because angle at the center is twice the angle at the circumference, subtended by the same chord. So there's two reasons for this one. Now again, looking at the one on the right, it might not seem obvious what you need to do, but if you think through the theorems in your head, for example, there's no cyclic or quadrilateral here, so that we can rule that out. There is something to do with the point at the center. There's been some sort of attempt to create an angle there. Now we know that the angle at the center is twice the angle at the circumference. Does the chord for the angle at the center, which is, that just disappear, is the red line, does this chord create an angle at the circumference? Yes, it does. So that means the angle at the center, let's just call that y. Y is twice the angle at the circumference, which is 70 degrees. Now I know that. I also know that this line here, that I've colored in red, and this line there is the radius. Radiuses are both the same length, so that forms an isosceles triangle. So essentially what I've got is an isosceles triangle with that angle there. I know that's 70, so 180 take away 70 will give you 110 degrees. And then we've got two base angles, so that's 110 divided by 2, which is 55. So your answer here for x is 55, and your reason is because angle at the center is twice the angle at the circumference, and then the second reason is base angles in an isosceles triangle are the same. So moving on to the next theorem, angles in the same segment are equal if they are subtended from the same chord. Again, you want to make sure you're writing all these keywords in the exam and you give your reason. Remember the chord here. So the chord for these two angles is that there. And if I just show you that, this chord creates, I was supposed to use the highlighter there. This chord creates that angle. and that angle at the circumference. And again, it also applies the other way around. So if I was to put a line here, we're also saying that this angle in green is equal to this angle in green. And it can come in different variations like I've shown on this. And again, you can see that in sort of action on GeoGebra. So if I was to move this, notice that they're both the same. They're both the same. So although the angles in blue are changing, well, they're changing in proportion. They're 95 and 95, the other two are 19 and 19. And now if I move the ones in blue, the ones in red are changing, but they're still exactly the same. It changes when you go into this sort of shape, because at this point it's a cyclical quadrilateral, but the rules apply all the way down until this bit here, okay? So, yeah, nice and straightforward. So all you would say here is x is equal to 60, and then your reason is going to be that angles in the same segment are equal. Well, you can get away with just writing that with this theorem, so you can literally just write angles in the same segment are equal. X here is 40 because angles in the same segment are equal, and obviously the long sort of definition of it is because they are subtended by the same chord, they're at the circumference. And again, if you look at this, cycle through the theorems in your head, and then you get x is going to be 108, and your reason is because angles in the same sort of segment are equal, and they're basically subtended by the same chord. I'm not sure why that's drawn an arrow. And again, if you look at this, we have got two angles subtended by the same chord in the same segment. So we are saying x is equal to 65 because angles in the same segment are equal. And now looking at this, now immediately when you look at this, I can see that x is going to equal whatever that angle there is. Okay, let's call that y. I know y and x are equal because angles in the same segment are the same. So in theory, I just need to find y. Now, if I do 110 plus 50, that's 160. If I do 180, because angles in a triangle add up to 180, that gives me 20 degrees. So that means y is 20. So that means x is also 20. And your reasoning will be angles in the same segment are equal, and angles in a triangle add up to 180. So two reasons for that one there. Now, again, with this one, that x there is equal to that y there, okay? Because they're both subtended by the same chord. So if I draw that line there, that chord creates that angle, and that chord also creates that angle. So if you were to look at this, we have 50 plus 30, which is 80. Again, I'm showing all my working out that I'm doing. And then I'm doing 180, take away 80, which is 100. And then I'm saying that, well, if y is equal to that, then I'm saying x is equal to 100. And then my reason, remember your reason, angles in the same segment are equal. Now looking at this theorem here, the alternate segment theorem, the angle between the tangent and the chord is equal to the angle in the alternate segment created by the same chord. Okay, so that seems like a little bit of a mouthful. So essentially what it's saying is, this theorem only applies when there's a tangent. So as soon as you have tangent, you can start thinking about this one. So there is a tangent. This angle in green here, created between the angle, between the chord and the tangent, is equal to this angle here, that's created by the same chord. So this chord here is what's used to create the blue angle. Okay, and because that chord also touches the angle between the chord and the tangent, it's equal. Now that might have sounded a little bit confusing, but again, I can show you that in action. So if you look at this shape here, so notice the blue and blue are equal, and red are equal. And essentially that's what this theorem is saying. So what it's saying is that the angle between the tangent, which is this line here, if I just move that there. So what it's saying is the angle between the tangent, which here is 40, is equal to the angle in the alternate segment that's created by the same chord. So if I go back and dive a tiny bit deeper into this. So if you look at, for example, the first one, where's the chord? That's the chord there, okay? And that chord is used to create this angle here, so they're both equal. The next one, where's the chord that's touching the angle between the tangent? It's that one there. Now, what angle does this chord create? That one there. Okay, now moving on to the next one. This is where it can get confusing, where it's one, what angle is the blue one equal to? Well, where's the chord that the blue angle touches? So the blue angle touches this chord. Now, what angle at the circumference does this chord create? It's the green one. So the green angle and the blue angle here are equal. And then the last one I've put in because it can really be a bit confusing. But again, step one, identify the chord. Hopefully that's easy. That's the chord there. And the chord is the one between that sort of blue angle at the tangent. And what angle does that create at the circumference? Remember, it's the angle at the circumference. So it's that green one there. So moving on. So here, x is equal to 50 degrees. And your reason, you can literally simply just state alternate segment theorem. Just them 3 words are good enough in the exam. Again, here, x is 42. And your reason, remember, it's alternate segment theorem. Ignore this line at the bottom. Now with this one, again, step 1, is there a tangent? Yes, so I can use that theorem. Where is the chord? Let's highlight the chord, okay? The chord is that one there. How do I know that's the chord? Because that's where this angle sits, the blue angle between the tangent and the chord, okay? Now, what angle does that chord create? Now, that chord creates this angle here at the circumference. So x is equal to 47 degrees. And here, x, where is the chord? So the chord is that there. What angle at the circumference does this chord create? So x is equal to 26. So yeah, just remember to state your reason on this as well. Now moving on, all I've done is sort of change the orientation here. And again, step 1 is to identify the chord. That's my chord there. As soon as you know where your chord is, what angle at the circumference is formed by the chord? Well, it's 42. So the answer here is 42. Remember to state your reason. Alternate segment theorem. Okay, you can just get away with stating that. And again, where's your chord? The chord is there. And the answer here is 38 because that's the angle the chord creates. So x is equal to 38 degrees. So moving on, I want you to press pause and have a go at these two because they can seem slightly tricky. And yeah, press play when you're ready for me to go through. So immediately you're looking at this, I know where the chord for 53 is. So x is equal to 53 degrees. And I can see for y, the chord is 89 degrees. Now, it might have been a little bit hard to spot for y, but if you should always start by looking at the tangent. And then, okay, if you look at the angle 89, what chord does the angle 89 touch? It's that chord there. What angle at the circumference does this chord form? It's that one there. Okay, and again, if you look at 53, what chord does that touch? It's that one there. What angle does that chord create? It's that one there. So it's going to be x for that. So looking at this one now, the chord that x touches, so the angle between the chord and the tangent. So we'll start with the tangent, look at the angle at the tangent, and then look at the chord. So the chord is that one there. We've identified the chord. What angle at the circumference does this chord form? That angle there, it forms that angle. It does not form 97 because although you can go up to 97 from the chord, you can't actually create the angle. It doesn't actually create it. That 97 angle is created between that and that. Okay, it is not created using this chord here. So x here is 42. And just moving on to some slightly different examples, we've already kind of covered this. So remember, when you're looking at this circle, no theorem necessarily applies, but remember your rules of circles. That's a radius. That's also a radius. Radius is always the same length inside the circle. So that means it's an isosceles triangle. That means this is also 30. And your reason here is base angles in an isosceles triangle are the same. So 30 plus 30 is going to give us 60. And then 180 take away 60 is 120. And then again here, this and this are the same. So that's 35, that's 35, and that's 70. So 35 plus 35 is 70 degrees. And 180 take away 70 is 110 for x. And again, your reason is because base angles in a triangle are the same. So moving on and looking at this one. So here for x, angles on a straight line add up to 180. Cool. Now that you have x, well, how do you find out y? Now, again, from the center, any line drawn from the center to the circumference is the radius. These two are the same. If these two are the same, effectively what we're saying is, well, that's 50. Those two are the same, which means if I do 180, take away 50, that gives you 130. And if I half 130, because base angles in an isosceles triangle are the same, get 65. So y is 65. And again, your reason will be for x, your reason will be that angles on a straight line are to 180. And for y, your reason will be that base angles in an isosceles triangle are the same. So again, looking at the one on the right, if you really think about this, any line from the center of the circle to the circumference is the radius. So that's a radius, and that's a radius. So straight away, you know this is an isosceles triangle, so that's 70. So if you do 70 plus 70, that's 140. And if you take that away from 180, you get 40. Okay, so you know that's 40 degrees, and then you're left with a straight line. So then to find x, so your reason 1 is angles in an isosceles triangle. Base angles are the same. Reason 2, angles on a straight line add up to 180. And if you do that, you get x at 140. And again, always sense check your answer. Does that look like it's 140? Yes, it does. And then sort of moving on from there onto this sort of tricky one as well. But again, you've got a straight line. So that'll be for x. Angles on a straight line add up to 180. Remember to state your reasons. That's 60. That was nice and straightforward. And now we know that this line here and this line here is a radius. So we know that that triangle with x and y inside it is an isosceles triangle. So if x is 60, well, angles in a triangle add up to 60. So you can do 60 take away 180, which gives you 120 and divided by 2. So you know that's 60 and that's 62. So you've already got y. Y is now 60. Again, your reason there is because base angles in an isosceles triangle add up to 180. And, are the same. And then for z, here you have to think a little bit harder. Now, you don't really. You could just go down the route of thinking, well, actually, that's also an isosceles triangle. But if you look at this, there's a theorem, which is angle formed from a diameter at the circumference is 90 degrees. So you could just say z is 60, 90, take away 60, is 30, and your reason would be angles formed from a diameter at the circumference is 30. You could have also gone down the other route and done it as an isosceles triangle, which is perfectly fine as well. Again, there is a question on the right for you to try, so press pause and have a go. So with this one, I can find z immediately because there is a diameter in this. So I can think back to the theorem about the angle at the circumference is 90 when you have a let's create by the diameter. So that's 90 there. Well, what does that help me do? Well, that helps me find z because I now know that this is 30, this is 90. So z must be 180. Take away 90 plus 30, which is 120, which gives me 60. Okay, so z is 60. And now with the other one, how do we find x? Now, from the center, any line drawn to the circumference is the radius. So that's also 50. So that then tells me that x is going to be 180, take away 50 plus 50, which is 80. And then finally to get y, that's angles on a straight line. So that's going to be 180, take away 80. Again, I've spoke through all my reasons, but you will have to write all these reasons down in the exam. And that's 100. And now we're going to look at this exam question. So this is a real exam question that's come up in the past. So with this one, now we need to find ADE, that angle there. Now there'll be multiple ways you could probably do this, but if I just look straight away at this and you're not too sure where to start because you've only been given one angle, you can always start off with what you know immediately before even thinking about theorems. Well, I know this triangle is an isosceles triangle because of them two lines. Well, what does that tell me? Well, that then tells me that this angle here and this angle here are the same. So if I was answering this in the exam, which is how I'm going to try to answer this, so BAD is equal to BDA, and my reason is because base angles in isosceles triangle are equal. So that then tells me 180 take away 40 is equal to 140. 140 divided by 2 is 70. Okay, so that's 70, that's 70. Cool. And then now thinking back to circle theorems, I know that there's 4 points that are touching the circumference. So this, I can use the cyclic or quadrilateral rule. So I can say that B, so if I just draw a line there, draw a line here, BCD is equal to 180 take away PAD, and that is 180 take away 70, which is 110. Okay, so I've straight away got that. Now again, you need to state your reason. What rule did you use there? So we're going to say that opposite angles in cyclical quadrilateral add up to 180. So that's the rule we use there. And then just using that 110, we can find this angle here because it's again a isosceles triangle. So if that's 110, that means if you do 110 take 180 take away 110, we get 70, half that and we get 35. Well, if I just get I do 170 by 2, I get 35. Again, your reasoning here will be that base angles in an isosceles triangle are equal. Again, you will have to state that in the exam, but in my case, I can just copy that and paste that down here. Perfect. So if I come back to the shape, I can say that's 35, that's 35. Now to get the angle of ADE, so it's angles on a straight line. So we've got essentially a straight line there. We've got 70, add that to 35, and subtract them from 180, and you get that angle come out as 75. So this is going to be 180, take away 70 plus 35, and that gives you 75. And your reason is because angles on a straight line add up to 180. And you can see how much I've explained each step, and I've written down the reasoning for it, except the last one. I've just spoke through it. And moving on to the next one. So with this one, there's two ways you can solve. There's actually multiple ways you can approach this. But again, look at this and think about what theorems do I know. Well, there is a tangent. There's, 3 theorems with a tangent. One is that a radius meets a tangent at 90. So immediately, you know that this angle here, I should actually use a different color. You know that this whole angle here is 90. So immediately I can do 53 take away 90, and I know that this here is 37. Okay? And the other thing I can already think about is the fact that this is an isosceles triangle, because the point from the center to the circumference is always the radius, so that's 37. Now, the other theorem I can straight away think of is the alternate segment theorem. And that tells me that the angle between the radius, the tangent and the chord is equal to the angle in the alternate segment. So essentially, when I look at this, the angle that would be created here is equal to this angle here. So I know what that angle there is. That's 37 plus 27. So using the alternate segment theorem, I know that's 27 plus 37. So if I do that, I get 64. And now, finally, to get ACO, which is what the question's asking for, well, it's now a straight line. Well, it is a straight line. So we have 180, take away the 64 that we found, plus the 53 we already knew in the question, plus the 37 that we found. We're going to subtract that from 180. So if I type that into my calculator, 65 plus 53 plus 37, that gives me 26 degrees. Okay, that is the answer there. Now, I have not explained the reasons here, so I'm just going to quickly talk through that. So reason one is going to be for this one here. That's OCE. You're going to say OCE is 90 because the radius meets a tangent at 90 degrees. Reason 2 is going to be that OBC, so that's this angle here, is 37 because angles inside an isosceles triangle, base angles are the same. And reason 3 is the alternate segment theorem, which is what we used over here in line with this angle here. And then finally, your reason will be angles on a straight line add up to 180, which is what we used here. And you will need to give all your reasons to get the marks. So here are some practice questions for you to have a go at. Press pause and have a go. When you're ready, press play for the answers. Remember to give your reasons. Here are the answers. Mark your work. Here's another set of practice questions. Press pause and have a go. Here are the answers. Make sure you've got the reasons as well. And finally, here are a set of challenging questions for you to have a go at. Press pause and have a go. When you're ready, press play for the answers. And here are the answers. If you found this video useful, please don't forget to subscribe. And as always, I'll catch you in the next one.